Hello everyone, welcome back to ptet.chemistry channel. So in this work number 3 as part of the 5070 chemistry curriculum, which is similar to the I forgot what's the called 0620 IGCSE chemistry for the 14 to 16 years old curriculum. So this is part of that ongoing lecture tutorials, and accompanying the lecture tutorials are these supplementary work that contributes towards further understanding of what we have done in the lesson itself. So this is propyl ethanoate is prepared by, so meaning to say this is the product. Prepared by means is formed by, is produced by the reaction between ethanoic acid and propanol. So you need to know that this is one of the product and this is another product, and obviously you know this product is water, which means this must be the other product, which is propyl ethanoate, and the name itself will make more sense once you come to organic chemistry later on when you reach year 10 or year 11, depending on whether you're on the 2-year or the 3-year program. So let me just make this a little bit tinier. So calculate the maximum mass. You want the maximum mass, so you want mass. You want the propyl ethanoate, which is this, that can be made from 7.20 gram of ethanoic acid. So this is actually ethanoic acid, and as part of organic chemistry it will make more sense later on. This is propanol. So you react between ethanoic acid and propanol, and you get these propyl ethanoate and water. So we have excess propanol. The fact that we use excess propanol means that never ever use excess for calculation, because it's not completely used up. So if that thing is in excess, if propanol is in excess, it means this thing is completely used up, and this is what we're going to use. If we look from the balance equation, what we are going to use is this ethanoic acid, and what we are going to be making is this propyl ethanoate, which is this product. So if you can look at it, you have 1 mole, because there's 1 in front and there's 1 in front as well. So 1 mole of this give you 1 mole of that. And what we could do is, if you think about what I've done in the lesson itself, I like to compare mole ratio. I like to write it like this. So this looks a bit tedious to write down, but I'll just show it to you. We write down n bracket something, because this represents the mole of this thing. This is a fraction over the mole of something. So the mole of something is to something. The first thing you do is from the balance equation. From the balance equation, the top bit, I have decided to put this thing here. So from the balance equation, there's 1 in front, so I put 1 there. And this thing I've decided to put at the bottom, there's 1 in front, so I get 1 there. Does it matter which way around it is? It does not matter, because if I have gotten them the other way around, let me see, if I gotten them the other way around, then what you would have gotten is, instead of that, instead of these, you will still get the exact same thing. Not really the exact same thing. If I just put this on top, and then I have another NCH3CO2H. If you read from the balance equation, the top bit is this thing is 1 in front, and at the bottom is for the ethanoic acid, and it's still 1 at the bottom. So it really does not matter how you write it, as long as you write and follow your own convention, follow your own writing. But it needs to be something that you know and something that you don't know, because you're going to be working out the unknown. So if I just remove that thing there, and hopefully you can see that when they are 1 to 1, then you can bring this up there and multiply by 1, and the 1 can bring up there and by this. Then you could see that these two must be equal to each other. If I just bring this thing at the bottom to this thing, simply because they are 1 mole is to 1 mole ratio, then I don't need to show the mole ratio anymore, because I just did it just now, and you could hopefully see that when it's 1 to 1 it's like this. When it's not 1 to 1, later on in other examples you will see we need to be more careful. Alright, so this thing, we are given the mass of it, which is 7.20 gram. So on the left hand side, this is called the mole of ethanoic acid. This is the mass of ethanoic acid, mass over mR. So this is mass over mR. The mass of the ethanoic acid divided by the mR of the ethanoic acid. So if I write down on the side my working, because we know how careless I can be, so that is 12 times 1 plus 3 times 1 plus 12 times 1 plus 16 times 3. These are all straight from your data, sorry, not data booklet, from your periodic table, which you need to be very, very familiar with. So mass in gram divided by molar mass, MR, in gram per mole will give you the mole, the actual mole of these. I want the actual mass of these, so I will have the mass of the propyl ethanoate. So there's product over the MR of that thing there. If I just work out the molecular formula, I have 1, 2, 3, 4, 5. I have 5 carbon. If I work out for hydrogen, 3 hydrogen atom, 4, 5, 6, 7, 8, 9, 10. So C5H10 or 1, 2, and there are 2 oxygen. So I just need to press my calculator. 12 times 5, 12 times 5 plus 10 times 1, and or it could be 1 times 10, doesn't matter. 16 times 2 or 2 times 16, I get 102. That is the MR of the product, and the mass of the product will be in gram, as shown here, will be in gram, but this thing is in gram, this thing is in gram, mass in gram over the MR of whatever thing that you are referencing. Okay, so if I just move this 102 up there, because you can do simple mathematics. So the mass of the product that you want is going to be whatever is on the left hand side. Bring the 102 up there, so times by 102. I want to show it to slightly more than 3 sig fig, because they want us to find answer to 3 sig fig. So 7.20 divided by 75 times 102, I get 9.792 gram exactly. 3 significant figure. 3 significant figure means I want 1, 2, 3. Then I look at the fourth one. The fourth one is lesser than 5, so it doesn't increase in 1. It's just 9.79 gram. This is 3 significant figure. You shouldn't try and run up before showing the examiner's the actual value, and it's also makes it easier for you to check your work if you actually list it down, so that you can later just press and pop on your calculator, and it's very easy to check your work. Question 2. So this is basically about the idea of MR. They use relative formula mass because this is a ionic compound. So it's about understanding the meaning of this formula, where there is 1 sodium, 1 iodine, 3 oxygen atoms, and then there is X number of H2O molecule, where in 1 H2O molecule you have 2 hydrogen and 1 oxygen, but you have X number of H2O. This is called water of crystallization, and water of crystallization, as I mentioned, is actually part of the 2023 syllabus in topic 7, if I'm not mistaken, under preparation of salts. I did cover it in class, where I cover this idea of water crystallization. This compound, it has an adjective, it's called hydrated, and when you heat it very strongly, you can remove all the water of crystallization. Then it becomes anhydrous, meaning you already remove all the water of crystallization. So they want us to find the value of X in this formula. They tell us the entire MR, which is obtained by summing up or by totaling the individual relative atomic masses, depending on how many you have. So what we are going to do here is have a look at the periodic table. So you have 23 for the relative atomic mass. This is the AR of sodium. You have 1 sodium atom. And then I have 1, 2, 7 for iodine, times 1. And I have 3 oxygen atoms, so there's 16 times 3. And then I have X number of water molecule. For 1 water molecule, I have 2 hydrogen, so 2 times 1, plus 16 times 1. It really does not matter if you do 1 times 2 or 1 times 16, as long as you've understood the idea of 2 hydrogen atoms, so it's 1 plus 1 or 2 times 1, and 1 oxygen atom, so it's just 16 times 1. There are X number of these water molecule. Very important to use the bracket like that. And this is equal to 288, because by summing the individual relative atomic masses, including the idea of X being X number of H2O for 1 NaIO3. Okay, so I'm gonna total them up now. 23 times 1 plus 127 times 1 plus 16 times 3 is equal to 198. 198 plus the 2 times 1 plus 16 times 1 is 18, so there's 18x. So 18x equal to 288 minus 198. I'm just moving the plus 198 to the other side, become minus 198. So 18x equal to 288 minus 198, that's 90. So x equal to 90 over 18. And in this water crystallization, you always have to get a whole number. If you don't get to the nearest whole number, you just have to round it up to the nearest whole number. In the theory paper, usually these are very nice number. It cannot be guaranteed, especially not in a practical setting where you could have a bit of experimental errors and you need to think about why the number could be slightly below the whole number, or why it could be slightly above the whole number, and we'll think about that when we come to alternative to practical as well as the actual practical itself. This next question is a very similar example, so without going through the idea again, so I'll just jump straight. This is the MR. So the MR is obtained by summing up the individual relative atomic mass. Very kind of them to provide us with this 59, but you can get it from the periodic table. This is element number 28. Nickel is element number 28. But the relative atomic mass is given in the periodic table. There is 1 nickel, 2 chlorine, and X number of water of crystallization. So 59 times 1 plus 35.5, which is the relative atomic mass of chlorine. There are 2 of them. I have X number of H2O molecule. So 2 times 1 because 2 hydrogen atom times 1, which is the relative atomic mass for oxygen. And 1 here refer to 1 oxygen atom times the relative atomic mass for oxygen. And I have X number of that molecule. So 59 times 1 is 59 plus 35.5 times 2. I get 130. And then I get 18x. So 18x is equal to 238 minus 130. 18x equal to 108. X equal to 108 over 18. And this is another very nice whole number of 6. Number 4, nickel is a transition element. So transition element or transition metal, sometimes they call them transition metal, is a big topic on its own that you will cover eventually in year 10 or year 11, depending on which type of program you're in. It's manufactured in a 4-stage process from nickel to sulfite. Nickel to sulfite is Ni2 plus and S2 minus. As you could imagine, plus 2 minus 2. When we construct formula, we bring down the number. The number is 2. The number is 2. The simplest ratio is 1:1 because you want the simplest whole number ratio of it. So there's 1 Ni2 plus and 1 S2 minus. The formula is NiS for nickel 2 sulfite. What do they want us to do? They want us to construct the balance equation for the reaction in stage 1. So I hope you're getting to see the idea of us doing balance equation prior to this. This is nickel 2 sulfite is heated in air. Air is a mixture of gases, most of which is nitrogen, N2, but then it also contains around 21% oxygen. As you can see, you get the nickel 2 oxide, the dioxide, meaning 2 oxygen. The oxide is O2 minus, Ni2 plus. Nickel 2 oxide is Ni2 plus O2 minus. So there is NiO. Sulfur dioxide, 1 sulfur, 2 oxygen. So not too surprising. It has lost the sulfur and that sulfur has gained oxygen. The nickel has lost the sulfur and gained oxygen. That's because it reacts with the oxygen in air, not the nitrogen. Alright, so A is a mixture. Nickel 2 sulfite plus the oxygen give us the nickel 2 oxide plus the SO2. Whatever equation you write, even when they don't ask you to balance, you've got to balance your equation. Alright, it's an international standard kind of thing. There is 1 nickel and there's 1 nickel. There is 1 sulfur and there's 1 sulfur. There are 3 oxygen atoms. 2 and 1 there. So altogether there are 3 oxygen atoms. I need 3 oxygen atoms there. So what I could do is 3 over 2. Some people really don't like fractions. If you don't like fractions, you can multiply 2 throughout. Then 1 times 2. 1 times 2 give you 2. 3 over 2 times 2 will give you 3 or 2. 1 times 2 give you that, 1 times 2 give you that. This is correct, this is also correct. You don't need to do both are entirely correct because you cannot change the identity of the formula, but you could change the number in front to include fractions, not decimals, fractions, which you could then simplify to the whole number ratio by multiplying by the correct number. Okay, so that is part A done. Well, 1 done. The next one is a calculation question. You want the mass of sulfur dioxide. As I mentioned previously, you gotta have balance equation. Wrong balance equation, you're gonna do the wrong calculations. Okay, this is 182 kilogram. When we do mole equal to mass over mr, we always say the mass is in gram because the mr is in gram per mole. Whenever you're given something in kilogram, when we compare mole ratio, this mass would most likely be in kilogram, and that would make your life easy. Because this is a structured questions, you can do it in kilogram, you can do it in gram. I am going to do in kilogram to keep to the same unit so that I'm not interconverting kilogram to gram and then the answer gram back to kilogram again. But of course you can choose to do it in gram as long as you can do the correct conversion. Okay, so let's get started. If I look at the balance equation, I want sulfur dioxide, which is SO2. This is nickel to sulfide. So I can see the mole ratio of SO2 is to nickel to sulfide. If I just do what I normally do in my other examples, this is 1:1, because if I put this on top, then I look in front of SO2, there's 1 in the balance equation, and there is 1 in the balance equation. How about if you use this, you will get 2/2, which can be simplified to 1/1, because 2/2 is equal to 1/1, alright? So that's from the balance equation. Now on the other side, what I'll do is, I will put in the actual reacting amount, which is mass over mr, okay? So I haven't gotten the mr of SO2 yet, I'm just gonna do it now. So there's 32 times 1, plus 16 times 32, 16 times 2, that give me 64. And I should very quickly do the nickel sulfide, which I think I gotten the answer on top there. Nope, nickel is 59, the relative atomic mass. So 59 times 1 plus 32 times 1, that give me 91. Okay, so what I can do is mass over mr, mass of SO2 over the mr SO2. So this is the mass of SO2. I'll just write in kilogram divided by the mr of SO2. So this is not exactly the mole of SO2 because this is in kilogram, but look what I'm going to do at the bottom there. This is given in kilogram, 182 kilogram of nickel sulfide. I've decided to put this at the bottom, but as long as you follow your labeling, if I put this at the bottom, then this refers to this from the balance equation. This refers to the actual reacting amount. So divided by the relative molecular mass, or mr, of the nickels to sulfide. Should I say nickel, relative formula mass, relative molecular mass, they both mean mr. They both have the same strategy of working out the mr. The mass that you're going to use is 182 kilogram. So that is 182, that is kilogram. I can only do this in kilogram if this is in kilogram. If this is in gram, then this is in gram. The unit will cancel out and it will still give you mole over mole. Okay, so if you rearrange that equation, I hope you can hopefully see the maths, but if you cannot, you can do it step by step. That is going to give you 182 over 91. If I bring out the 64, what I'm going to get is the mass of SO2 in kilogram is 182 over 91 times 64. I believe I'm starting to run out of space, so what I can do is I can move this up a little bit, and hopefully we can save a bit more space. And that is not looking good at all. That's looking better, I guess. No, not really. Anyway, pop that into the calculator. 182 divided by 91 is 2 times 64. I get 1 to 8. Unit is very important. I already started to label it from the very beginning because I know if I don't label things, I will lose track of what I am doing. Once you lose track of what you're doing, you're losing the story, you're losing the plot because you refuse to label. And that's how I get the answer to be in kilogram, because this is a quantity in kilogram, because I've decided to use this in kilogram, so I put this in kilogram rather than making my life complicated. But you could do and get it in gram, and then you get 128,000 gram. Moving on to the next question. So we have zinc, which is blah 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 blah. We have one salt, which is a hydrated compound. Hydrated compound has water of crystallization. So all of these was mentioned in my lecture tutorial, which you could revisit, of course. So crystal of zinc sulfate, you can prepare zinc sulfate. Zinc sulfate is what you call a salt because it contains a sulfate ion. This is called a sulfate ion. So we are essentially looking at formula. So that's what they want. They want formula. Don't know why it showed me as jagged stuff there. So they want formula. They want compound. So they want compound. So you can't use the metal itself to give you metal salt. Of course, metal plus acid will give you, reactive metal plus acid will give you metal salt and hydrogen. But they want compound of zinc. So we can be thinking about the carbonate. So metal carbonate plus sulfuric acid or any acid will give you carbon dioxide and the metal salt and water. And the other one you can be thinking about would be zinc hydroxide. So zinc hydroxide can react with an acid to give you salt and water in a neutralization reaction. Potentially, eventually after you have learned more about metal oxide, so zinc oxide could also be another compound of zinc that can definitely react with dilute sulfur acid to give you the salt as well, because zinc hydroxide can come from zinc oxide itself. All right. Part B is basically about the experimental strategy, experiments involved in order to work out the value of X. So you're going to heat it very carefully to drive off the water. One of the most important things that a lot of 14 to 16 years old students don't realize is that you don't just put the test, you don't just heat the solid straight away without a tube, but you don't just weigh the tube and the heated solid on its own. You gotta have the mass of the empty tube, and you do these before you do all of these, because you can't just tip out the solid and weigh the mass of the tube itself, because there's bound to be some solid left in there. So you gotta do it at the beginning of an experiment. So that's why you weigh the mass of an empty tube. All of these are masses, and masses. So you need a balance. We call them a mass balance. A mass balance basically measures, well, it records masses. These are mass balance that record up to 2 decimal places, so they are fairly accurate. And they're asking you, why was the boiling tube heated? Let it cool, and then reweigh again 4 times. Okay, so you want to reweigh 4 times so that after the 4th heating, you want to heat it to a constant mass, because if this is what you started with, the hydrated salt with the tube, the anhydrous salt after the 4th heating with the tube, this means there's no more changes after the 4th heating. If there are no more changes, there are no more water being driven off. So this must be just the anhydrous zinc sulfate plus the mass of the empty tube. So the whole idea of doing it 4 times, you know, heating, cooling, and then reweighing, heating, cooling, reweighing, do that, repeat it 4 times, is to ensure that all the water of crystallization have been driven off. So this experiment is based on this equation. So you want to make sure that none of that H2O still remains as this. So you want to ensure all the water of crystallization has been driven off, has been removed, has been eliminated, whatever word you like. Okay, has been removed, has been driven off. Okay, so this is called heat to constant mass. So sometimes the question will say, what should you do to ensure that your experimental strategy is as valid or as accurate as possible? You want to heat to constant mass so that you reweigh after the second, the third, and the fourth, it gives you the same value, because there's no further change in the mass when all the water has been driven off. Now they want you to calculate the amount in moles of the anhydrous salt produced. So first of all, you need the mass of the anhydrous. The anhydrous meaning all the water have been driven off. So you want the mass of these. This is the result after all the water has been driven off. So this 76.34 is this plus the tube. So to get the mass of this has to be minus the mass of empty tube. So it's 76.34 minus 74.25. A lot of these things at this level is all about understanding if you are doing this on your own, how much of it do you understand, what results you'll be recording, and how to interpret results. These are masses. Masses have grams. Well, these masses have grams, their unit. We must put down units because that's what we are doing. Okay. We need the MR of the zinc sulfate because that is the anhydrous salt, ZnSO4. So off you go to your periodic table. You have zinc, which is 65 times 1. And then you have 32, which is the AR for sulfur, times 1. You have 4 oxygen, so 4 times 16. You get 161. There's the molar mass. So what happened then is the mole, if I just use the short form, N bracket ZnSO4 is going to be mass over MR, and that is 2.09 over 161. Give me a pretty ugly decimals. So how many decimal places should I run up my answer to? You see all these data? These data are given to 1, 2, 3, 4 significant figure. All of these are 4 significant figure. So I can leave them to 4 sig fig, but I should really put one more sig fig here from my calculator. 1, 2, 3, and 4 sig fig, because the number in front, if it's 0, it does not count as significant figure. So this is the first, second, third, and fourth significant figure. So this is my fifth one, is lesser than 5, so I can run it up to 4 significant figure. This is small. Now the next one is I want the mole of water driven off. So this is anhydrous solid. This is this plus the tube. This is the tube plus the hydrated solid. When it is hydrated, it has the XH2O. When it is anhydrous, it has got no XH2O. So the difference between this and this is going to be how much water has been driven off. So 77.97. So mass of H2O driven off. So a lot of the times, a lot of students just like to write 77.97. A lot of the times, students just like to show the working, and in all honesty, you might understand your own working, but when someone put yourself in the shoes of the examiner, someone else might not understand what they are doing unless you label it properly and let them see what is going on. So they want the moles. I'm going to calculate the MR of H2O, which you have done so many times, and it's 18, but it's good to just do it, just to see it. So you have the mass divided by the MR. So there's 1.63 gram divided by 18. Again, there's 0.090556. So to 4 significant figure, we don't count the number in front. This is 1, 2, 3, 4. We count the 0 here because this is in between other numbers. So this is first, second, third, and fourth. So you look at the fifth one, it's more than 5. So you have to add one more. So 9056 mole. This is to 4 significant figure. Now use your results to calculate the value of X. Now this is X. This is mole of H2O. This is mole of ZnSO4. This represents 1. So 1 mole of zinc sulfate is to the mole of H2O. So what we could do is, the mole of H2O over the mole of zinc sulfate, from the formula itself is x over 1 from the formula itself. Now equal to, put in the actual data. The actual data, the mole of H2O is 0.09056. That was your answer to part 3. Your answer to part 2 was the mole of the anhydrous salt, 0.01298. 0.01298. Just double checking. So there was the anhydrous salt, there was just the zinc sulfate. So there was just the zinc sulfate there. So if you could see there's 1 there, you could just move the 1 up there and it will not make any difference. So if you just do 0.09056 divided by 0.01298, this gives me 6.977. Again, this has to be a whole number. If you look back at work 2, or was it, I think it was work 2, no, probably not work 2, probably in one of those examples from molecular formula, just in the last lecture tutorials, this thing were mentioned to be a whole number, and these things are from experimental results, so you know they are not perfectly a whole number all the time. So the nearest whole number is 7, and just like that you get the 7 marks in these kind of very simple calculations just by comparing mole ratio. For part C, so this is looking slightly complicated. Well, it makes sense for it to be the last bit of the question, for it to be a bit harder. So they've given you the MR of zinc ethanoate. So they've given it to a slightly greater accuracy, more than the whole number T as given in your periodic table for O-level IGCSE level chemistry. So now you know you want a dose of 15 milligram of zinc. You want 15 milligram of zinc, and you want to know in zinc ethanoate, which is this thing here. So that is zinc ethanoate. I don't want to circle that, just probably underline it. Okay, so what is the percentage by mass of zinc in the crystals? How many zinc do we have? We only have 1 zinc, because all of these you have 2 of it. You only have 1 zinc, so it's 1 time. How many zinc do you have? We have 1, and the mass, the relative atomic mass, the AR of zinc is 65. So the AR of zinc is 65. The MR of the crystals, meaning to say all this thing, if I just, oh well, actually they give us the MR already, so there's no need to calculate that. So it's divided by 219.4. That is actually multiplied by 100%. So 65 divided by 219.4 times 100%, they give me 29.6%. So this is 4 sig fig, so maybe I can round it up, 29.63%. But that is the percentage by mass of zinc in the crystals. What do I need? I need 15 milligram of zinc. I need 15 milligram of zinc. So if okay, if 29.63% is 15 milligram, therefore 100% must be a lot more than 15 milligram, which is 100 over 29.63, because you want to know out of the whole thing, of which only 29.63% is zinc. Out of the whole thing, the mass is going to be a lot more. So 15 times 100 divided by 29.63, you need, give or take, around 50.624. So 50 they've given us 15 milligram, so perhaps I can run it up. I'm not comfortable running up to 2 sig fig when this is 4 sig fig, this is 4 sig fig, this is 2 sig fig. Give or take, I'll say 3 sig fig. There is a good compromise. So there is 3 significant figure. Out of 50.6 milligram, you can do 65 times 1, because you have 1 zinc atom only, divided by the MR times this, you're going to get 15 milligram of zinc, which is the dose that you need for 1 day. All right, so just a bit of wording, just a bit of maths to get you thinking about out of the whole 100%, which is a lot more than that 50 milligram, you need to take this much, because out of this much, only about this much contains zinc, which is the 50 milligram that you need. Let's think about the next problem. So instead, if you don't take as a solid, you take as a solution, you have a 5 cm³ of the aqueous solution. So I guess by this stage, you would have done concentration in mole per dm³ times the volume in dm³ is equal to mole in mole. As you can see, mole per dm³ times dm³, the dm³ and the dm³ can cancel out, and that will give you mole. Okay, so concentration in mole per dm³ times volume dm³ give you mole. So if the dose is taken at 5 cm³ of aqueous zinc ethanoate, what would be the concentration of the solution used? So if instead you take as a solution, and you still want 15 milligram of zinc, okay, this is zinc ethanoate, so the MR is 219.4. Let's think about this. Actually, in hindsight, I think this is useless because this was for part 1, this is part 2. This is aqueous zinc ethanoate. This was the crystalline zinc ethanoate in water. So once you dissolve it in water, it's not going to be this exactly, because the water is going to go into the water, okay? So I could be thinking about this as the zinc ethanoate itself. So what we could be thinking is just zinc and then CH3CO2. So if I just do this minus 2, do I really need this? Probably not. Okay, let me try and think about this again. What do I need? Okay, so we know we need 15 milligram of zinc. That 15 milligram is of zinc, not of zinc ethanoate crystals, not of aqueous zinc ethanoate. We need 15 milligram of zinc. Okay, so if I look at the formula, one of these zinc ethanoate, the mole of zinc is equal to the mole of zinc ethanoate. If you look at the formula of zinc ethanoate here, there is one zinc to give you this compound that has one zinc in it. So in the whole compound, there's only one zinc. Therefore, the mole of zinc is equal to the mole of that, because you could be thinking about the mole of this thing, the crystal, over the mole of zinc. In one of that, how many zinc do you have? You have 1. So these are mole of the crystals. In 1 mole of the whole thing, you only have 1 zinc. So that you can get them to be equal to each other, like that. And since they are equal, remember this is your concentration times volume. Why? Because this is aqueous, but this is your solid. So this is going to be your mass of zinc over your AR of zinc, because this is the 50 milligram of zinc divided by the relative atomic mass as given in your periodic table. So that is equal to concentration of the zinc ethanoate times the volume. This is volume of solution in dm³. This is concentration in mole per dm³. You will see that mole per dm³ times dm³ will give you mole. Gram divided by gram per mole, mass of AR will give you mole. So we are not breaking any mathematical rule at all. So the mass of zinc we want is 15 milligram. So 15 milligram convert to gram is times 10 to the minus 3, because you are converting 15 milligram to gram. So you either times 10 to the minus 3, times 10 to the minus 3 is equal to divide by 1,000. So this is just a mathematical term. Either you do that or you sure divide by 1,000. I personally like this because it's what you do in maths anyway. Have a look at your periodic table. Zinc is element number 30, so the AR is 65. The concentration of the solution used, they want in mole per dm³. I've done this mole per dm³. If I don't have the stroke, then it's just mole dm minus 3. because mole dm minus 3 means mole per dm cube. Okay, this is another mathematical expression. This thing here is exactly the same as mole per dm cube, mole per dm cube. Okay, so that is what we want, the concentration in mole per dm cube. What is the volume? The volume is 5 cm cube. So 5 cm cube convert to dm cube, 1000 cm cube, by the way, 1000 cm cube equal to 1 dm cube. So 1 cm cube equal to 1 over 1000 dm cube, which is the same as 10 to the minus 3 dm cube. So what I could do is the volume, which was given as 5 cm cube, so I could do 5 cm cube times 10 to the minus 3. This becomes dm cube. Therefore, the concentration in mole per dm cube is equal to 15 times 10 to the minus 3 over 65 times 5 times 10 to the minus 3. So I'm just bringing this down there, it becomes divide. So this divide by this is going to be this times 1 over that, and hopefully you can do the maths. If you can't, do it step by step, and if you still can't, I suggest you talk to a maths teacher who can try to help you and see these things clearer. But a bit of mathematical improvements required on your part as well, right? So since I left the previous part to 3 sig fig, then I'll leave these to 3 significant figure as well. So this is mole per dm cube. Okay, so this question looks complicated, but I like it because it's to do with reading the question, it's to do with thinking about the units, and it's to do with thinking about mole of a solid and mole of a solution. Alright, so that's it for this work 3 tutorials, and if it's been useful, so do subscribe to the channel and share the channel widely with others. Alright, so if you've got any questions, do raise it up and let me know. Thank you for watching.